Hello, I'm Sarthak Chakraborty, and I'm going to give a brief summary on our work Causal Graph for Instance Level Microservice Data. In production systems, monolith architecture of system design has been replaced by the microservice architecture, which comprises of multiple interconnected distributed services, where each such service performs a dedicated task. Such an architecture helps in a more scalable, flexible, and manageable deployment of a large and complex system. However, such a large system of services is bound to be vulnerable, and it is of utmost importance to maintain the availability of such systems in production to reduce the revenue loss. As an example, during the 2020 authentication outage in Google, they lost a staggering $1.7 million in ad revenue. A common starting step for diagnosis of these microservices is to understand the structure of the system using causal graphs. A causal dependency graph between the important KPI metrics of each service is built that denotes which metric of a service causally affects which other. A causal graph can then be used to localize faults and detect root causes. In practice, usually multiple instances or nodes of the same service are spawned for load balancing and reliability purposes. An autoscaler adjusts the number of instances based on the incoming load. These deployed instances are, however, unique, and thus, once an instance with a specific hardware gets killed, probability of the same machine being respawned again is very low. Secondly, these instances are transient in nature and last for only a short span of time. For example, one of the production service in Adobe spawned around 1,000 unique instances over 3 months with an average life of just 6 hours. Now the question is, how do we incorporate these transient dynamic instances into account while estimating the causal dependency graph of the entire microservice system? One approach is to aggregate the metrics over all instances of a service for each time step. Thus, we get a single aggregated value for each service metric, and the problem then boils down to the known literature of causal structure estimation. However, aggregating these metrics reduces instance-specific variability in them and hence results in wrong estimation of the causal graph. A wrongly estimated causal graph can result in a faulty evaluation of a downstream task that relies on it, for example, a graph traversal based root cause detection. Hence, in this work, we propose a causal graph estimation technique named CausIL that takes into consideration these metric variations within instances of a service into account while constructing the graph. It also implicitly captures autoscaler decision by modeling the transient and dynamic nature of the instances. We have also utilized generic system domain knowledge to boost the accuracy and improve time complexity. To know more details of our work, please attend a session. Thank you.